Talking about driving forces. We want to decrease the energy, either internal energy or H. We want to increase the entropy for chemical reactions, but sometimes there's a conflict. Sometimes there's a And so what we want to do is we want to be able to quantitate, put some numbers on the entropy, rather than just qualitatively look, is the entropy going up or going down. And so to quantitate the entropy, we need to determine the absolute entropies. Did I talk about enthalpy and internal energy, absolute enthalpy? And those can't be determined, right? Or those typically aren't determined. They can be determined. They can be estimated, but absolute entropy is not a problem to determine. So this is unlike absolute enthalpy and absolute internal energy. These typically are not determined. Some people will do some theoretical calculations to estimate it, but the errors in those calculations are quite large. Absolute entropies can be determined by looking at heat capacities. And so it's a little bit more complicated, but they're related to heat capacities. C. We'll do it at constant pressure. Most reactions that we do are constant pressure. And so it's related to heat capacity. And so what we do is we just measure the heat capacities. Did I talk about this already? Yeah? It's the area under the curve. So I forgot. I got past this. Let's go. And it makes sense that entropies are going to be related to heat capacities, because the heat capacities tells you, how much energy can be absorbed by the substance. And things that have high heat capacity can absorb a lot of energy because they have a lot of what? Things that have a high heat capacity can absorb a lot of energy because they have a lot of ways of, let's say, dissipating the heat, or a lot of ways of absorbing the heat. They have a lot of ways of absorbing the heat. So for example, water has a fairly high heat capacity because, when you heat up water, water can rotate, it can vibrate, it can translate, and so you gotta have all those motions going on. And then, whereas heating up copper, you just have vibrations, and those vibrations are locked in the lattice. Okay, and so it's related. So we talked about, did we talk about this? Did we talk about, if I look at the heat capacity versus temperature for water, solid water, ice, has a fairly low heat capacity, then it jumps up to liquid water. So this is solid, this is liquid. But then it goes down for gaseous. I talked about that? And so why is it that, which one has a higher entropy? Why does the entropy look like this? The entropy for solids is lower, for liquids it's higher, and then for gases it's even higher. And so gases kind of have a low heat capacity, but they have a high entropy. Why is that? Well, one one reason is it's a cumulative thing, because when we look at the area under the curve, when we look at a gas, the gas is going to have a lot of area under here. And the entropy, the absolute entropy, is proportional to, this is, in calculus, this is an integral sign. Integrals just take the area under the heat capacity curve at a specific temperature from 0 up to the temperature of interest. So if we're interested in this temperature here, we have to go all the way from 0 and get the entire area under that curve. And so this is just the area. And so gases, they're going to have a higher entropy because it's this cumulative thing with the area. So that's the only thing. And so we can get the entropy of water at many different temperatures. That's a lot of data. If you just wanted one entropy for water, you know, which entropy would you want? Would you want the entropy at minus 43 degrees C? What do you think would be the most useful entropy to know? At what temperature would it be? Well, we have all these data, actually. Although we didn't, did we measure the heat capacity at absolute 0? No, but what they do is they just extrapolate the curve out. You know what the entropy is at 0? The entropy is 0. Yeah, there's no motion, and water should form what we call a perfect crystal. And so the lowest entropy possible is 0. We can't have negative entropies, can we? No. No, because from the Boltzmann equation, we saw that the fewest number of ways of arranging the system is, what is the fewest number of ways? Is it 1 or is it 0? Can you have 0 ways of arranging your bookshelf? No, the fewest would be 1, you know. You have everything, it has to go in a specific place. And so 0 is going to be the absolute 0 of absolute entropy, right? I mean, we aren't going to have any negative. And so this is just going to be extrapolated out. You know, we'll have data. So we could have this, but probably the most useful temperature to know the entropy of is yeah, but if I wanted to compile, because we don't just work with water, we work with a whole bunch of substances. And if we have a huge data table just for water alone, well, that's too many numbers. It's going to get too thick, our data table. And so if we're going to just pick one temperature, what would be the most useful temperature? Would the most useful temperature be maybe 0 degrees C? Remember STP for gases? You'd say room temperature? Yeah, is STP going to be really worth it for us? No, not at all. And so, excuse me, we're going to go with room temperature, which is 298 Kelvin. And so the entropy of 298 Kelvin is one we want, and so we'll get a whole bunch of different substances and then just compare their entropies at 298 Kelvin. But anyway, for this, a lot of different substances and a lot of heat capacity measurements were done, and then we generated a table like this in Appendix D. So let's take a look at the table.